Okay, let's get started. Thank you everyone for joining the afternoon session about the hands-on lab application development. So in this session, we'll be going over a custom application development and more specific, a self-consumption algorithm. And we'll run this application at the end of the demo as well. So yeah, let's dive into it. Here a short overview of what I'm going to be talking about in this session. So first of all, what we'll program today. I'll give you more information about the self-consumption algorithm that we'll be implementing today. Second of all, I want to give you a quick overview about the lab the configuration, because this is what we're going to be controlling. And then, of course, number 3 will be building the actual application itself. At the end, we'll have some time for Q&A as well, so please feel free to post your questions at the end of the session. Yeah, first, let's dive into what we'll program today. So I'll give you a demo of how to implement your own self-consumption algorithm. So the self-consumption consumption algorithm is more like a smart energy management system that maximizes the use of your on-site renewable generation. So what it will do is we'll prioritize local consumption of solar power. If there is excess solar power, it will store this excess energy in your batteries to be used later on. And it will always meet your load demands. So that way we minimize your grid imports and reduce the cost of importing power from the grid. And of course, it boosts your overall renewable energy utilization. So that's what we'll be implementing today. Before we dive into the actual demo or the actual configuration, I want to show you the lab again, what we're configuring. I've already showed the same lab in the previous demo, but I want to do a quick recapture of the things that I've talked about before. So let us go over to the D-side single line diagram about our lab 2. Worth mentioning already is, so in our lab 2, we have a couple of key components. First of all, there is our battery, our 256 kilowatt hour LG battery. Then we have our two 30C3 parallel converters. So they work in parallel for more redundancy and increased capacity in our lab. Then we have solar, our 20 kilowatt DC coupled solar arrays with amped optimizers, and we have our DC loads like the lighting, our EV charger, and the fan. So let's go over the single line diagram one more time so that it's clear what we're going to configure here. So here we are, single line diagram of our lab. So I talked about the LG battery is the one at the bottom right here, our 256 kilowatt hour battery, connected in parallel to our two 30 kilowatt converters. So it's a 3-port converter, one AC port, 2 DC ports. One DC port is connected to our 350 volt DC bus and our DC panel here in the middle. And the other port, the DC3 port, is connected to our LG battery. Then, of course, on the AC side, it's combined in a panel, and we have a net meter as well to measure the net power coming in, flowing in, and flowing out to the grid. On our 350 volt DC bus, what we have too are our DC coupled loads. So we have our EV charger, our DC EV charger, and our other loads being the fans and our high bay lights running off of 350 volts DC. Last element here are the solar optimizers from AMD. So these are injecting our solar panels from our solar arrays. We have solar panels of 265 watt each 3 panels in series, and each AMP optimizer can take 2 strings as input and 1 output. So this is a quick overview of the lab and the setup that we're going to configure. Over to my slide. Okay, and then the actual building of the application itself. Again, we'll start from the documentation. Everything what I'll be explaining here, the boilerplate, the built-in functions can all be found in our online documentation. And then, of course, same thing as before, what we did for the setup and configuration. We have a publicly available GitHub repository, which you can fork and clone and start working from on your own. And we also have a boilerplate code that can help you start from that. So let me quickly move over to the documentation and let you show where you can find all this information. So in previous sessions, we have covered the installation, we have covered the file configuration as well. Now in this phase, we're actually focusing on the custom application. And again, everything is explained here as well. So we have our PPL app repository, which you can start from. So forking from the GitHub repo or publicly available GitHub repo and cloning into your own Visual Studio code editor that helps you get started and working on your own custom application. So this is all available right here for repository, clone repository. I will be talking about this in any minute, but here you can find any additional information if something is not clear. Okay, let's get started. Again, we'll start from cloning the GitHub repo. So let me go to the publicly available GitHub repo that we've set up. Same thing here. We'll start with forking this repository, which means is you'll create a exact copy of this repo into your own GitHub account. So what you want to do here is click fork repo. You can give it a name. You don't have to use the PPL app. You can use any other name here for your repo name. And then you say create fork. So now you've effectively created a copy of that demo repo or that PPL app repo into your own GitHub account. And from that point, you can start working on this, modifying, changing files, and writing your own application. So in the next step, what you want to do is clone this. So what I always use is a code editor on my local laptop. I use Windsurf. There's also Visual Studio Code that is available out there to help you start modifying these files and create your own application. So let me go ahead and do that. So what you want to do now is clone this repository to that code editor that I was talking about. So you go to this green button. It says clone this. You can copy this URL. This is the one that you need. And then you can open up your Windsurf or your other code editor on your laptop and start from here. What you want to do, so you copy that URL that has your personal GitHub repo, you go to clone repo, you add it in here, and you hit enter, and it will clone it repo into your local folder. I won't do this because I already done this before, so this is what it will end up at. So here you have that PPL app demo repo that I was talking about. And now we can get into the coding of that actual application. First of all, we will start from a boilerplate. So in this repo, I've included a boilerplate that's available for all of you that helps you get started. And let me quickly go over a couple of the items here that are included. So first of all, here is the main function. The main function, what it will do is in a first step, it will create a connection with the controller. So we also talked about in the previous sessions is our controller, which is the Power Platform controller, uses NATs to communicate, for example, with a third-party application or third-party EMS. So this is what we're developing right now. The controller runs a NAT server where we can subscribe to, we can get the measurements from the control, but we can also send commands to the controller. And it's all regulated by this NATS interface between the controller and the third-party application, being our own application now. So NATS client on the third-party EMS side, NAT server on the controller side. So this is what the first lines of code are here for. So this PPL app will create a NATS client connection to the NAT server on the controller. So, and what it needs for that is the controller's IP, the username, and the password. That username and password are the same ones as we've defined previously in the config.json file. So in our previous hands-on lab where we discussed the setup and configuration, one of the things that we've configured is a config.json file, and part of the config.json file was the local NATS connection. There we could modify and update the username and password, and these are the ones that we also want to use here. You can type them in directly here if you want. But you can also, what I prefer to do is use an environmental file, which is the one over here, which has all this information available. So it contains the IP address, it contains the NATS username, and it contains the NATS password. So rather than hard code it into one file, I prefer to use an env file because if you're writing multiple applications and you're changing username or password, for example, on your controller, you don't have to change it in every other application that you're developing or writing. You can just change it one time in your env file, and all your other applications here will use that same and modified username or password. So this is the main function, and this is where the NATS connection is created and started up. Then we have a startup delay for the NATS connection to make sure that it's correctly established. We'll introduce a startup delay. I have a startup delay of 5 seconds. Can be more, can be less, but this is what you can do. And then the main function is actually right here. It's the true loop where we will effectively every time run that PMS application, what we will be defining in this session. So if you look at the PMS, what it consists of, so now it's still an empty. So this is to give you an idea of what you can do. So you can start writing your functions in here in this boilerplate and use helper functions to do so. So you can write your code, you can start writing your code in here, but you can use or define helper functions in order to make sure that your main code, your main PMS code does not get too crowded and too overcomplicated. Okay. This is a quick introduction about the boilerplate. For the self-consumption algorithm that we're defining now, I've created another boilerplate that has some more information. I added some extra helper functions that can get us started with building the actual application. So same thing is here. We have our main function in this part of the code. it's always the same. So it uses the IP address, username, and password to set up a NETS connection with the controller. Small difference here is that I use a class now to define our self-consumption algorithm. This is easier to use your functions and use that app in your class itself because it's made available everywhere with the self constructor. So slightly different, but in principle, it all works the same. So instead of here, the PMS function that we have here, I'll call the self-consumption class that I have made, and I'll use the execute function. So this is how Python and the classes and modules work here. So it's pretty easy and straightforward to use. So okay, let's dive into it, and let's start modifying the execute function, which is our main function. So overall objective here was to create a self-consumption algorithm. And what I said with self-consumption algorithm is what we're trying to do is minimizing the grid import. And so we don't want to have any power flowing in from the grid in this case, so that we can maximize our self-consumption, maximizing our on-site solar generation and storage. So let's start with that. And what we need for that that grid power to determine is we need to have the grid power first. So we want to know what at every point in time what the grid power is. So I created that helper function that is a function over here on line 25 that says get grid power. So what I'm gonna do is I'll assign grid power to self.get grid power. So I'll execute that function, and that function will then return my grid power here. Of course, this function is not yet defined, but we'll do so right now. So the get grid power function, what it actually needs to do is it should return the current grid power from either a net meter or the sum of the converter AC ports. Remember, in our example, we do have a net meter right here. So we have the two options available. So we could either use the measurement, the power reported by the net meter, or we can use the sum of the port 1 powers of your both converters. It might depend on your application whether you need a net power or not. So for example, in our case, we don't have actually AC loads connected to our lab. So all of our loads are DC coupled and are all running off the 350 volt DC bus. If you would have AC loads and you want to make sure that this is included in your self-consumption, then you would need an AC net meter to make sure that you can limit that grid import power from the grid. So yeah, let's start with that, implementing that get grid power. So first of all, I'm gonna do this if net meter active. So we'll define a variable or a constant in your function that says if your net meter is active, what we'll do, our grid power is actually we will get it from the net meter. Now we have our first thing that we need to make sure. So we need to get the grid power from the net meter in here. And let me go back into the documentation since it's explained here. So that PPL app function that you've seen before, where I said this creates the nets connection between your custom application and the controller, it has some built-in functions. So one of them is the get all measurements. This app.getAllMeasurements, what it will do, it will return a dictionary with all the measurements in your that your controller has. So that can be a converter, that can be a battery that we've defined, that can be a solar optimizer. This will dump all these measurements in here. But if you're looking for a specific measurement here, what you can do is not use the get all measurements, but the get measurement function. And what that get measurements function needs is a device ID and a register name. So for example, right here, example for method port 2, what we do is we say, hey, app.get measurements from the device ID converter 1, and we'll say we need this register name. Remember again, these registers, the register names that you put in here should be the same ones as you've defined in your address map of your respective device. So you may need to make sure that in your address map of your converter 1, there is a register called measure.ports port2.method. Otherwise, this function will not work. It will not return any results. So that's the only remark here. Make sure that your register name is defined in your address map of this device, meaning the converter 1. And then the same thing goes here. If you want to return the voltage of port 2, same thing goes here. You type in your converter ID or device ID and your register name. So this is what we are going to do here as well. So you want to return the grid power here. And since I've defined a class self-consumption, the app is available in self.app. So we do self.app.get measurements, and we type in the device ID, and I'll also make a constant of this device ID because it will not change. So let's call it meter ID. And in my case, it's defined in my device.json file, and it's called the net meter. So what I can do here is I can click on get measurements, type in the device ID, which is my meter ID, and then type in the register that I want to use or return. That is measure.ports.port1.power. So with this function, if the net meter is active, and I also need to define this constant here, net meter active. You can set it to false or true. If that net meter is active, the grid power that I want to return comes from port 1 power of my meter. So this is the first thing. So when we do have a net meter and we want to use a net meter power for our self-consumption algorithm, this is what we do. Else, what we can do, if the net meter is not active, our grid power is actually, like I said, it will be the sum of the converter AC and DC ports. So our grid power is a sum of the self.app.get measurements of the converter ID1 and I also need to define this constant at the top, and I want to use the same register here because it's defined in my converter ID1 address map measure.ports of port 1. Again, make sure that these registers are always defined in the address map of the device that you mentioned here. So we have defined our converter ID1, and in my case, this is in my devices .json file, and it is listed as converter 1. And then same thing we can do for converter ID2, which is converter 2. Because like I said, if the net meter is not active, we want to use a grid power, which is a sum of the self-amp get measurements. Is this one? Okay. So it's a sum of get app measurements of your converter ID1 and your converter ID2. So this is our grid power. Let's this one up. So our for net meters active, grid power is meter ID, And also we'll define the grid power as a sum of our AC port power for both converters. And then what is left for us to do is return this grid power from this function. So what we did now is, so we defined the get grid power function. It will determine the grid power at any moment in time, and it will store this here in our grid power function. Next thing that we want to do is define our power set points. So power set points, what I mean by that is, so we want to minimize that import from the grid. And what we can do is control our batteries. So to either charge or discharge more to make sure that it covers the load. For that power set point that power set point needs to be applied to somewhere. And in this case, it will be at the battery port of the converter, of both converters, because these two converters are working in parallel. So what we want to do is define the power set point. And we have defined that power set point is, we can always, so we start with a power set point of 0 at the start of our application. But in order to minimize grid import from the grid, what we can do is use that power set point and add our grid power to it. That way we can minimize or reduce our grid power to 0, because it will be the remainder of your power set point and grid power. So in that way, your power set point will be increasing or decreasing depending on your grid power. So if your grid power becomes more, so we import more, our power set point becomes more, which means we will discharge the batteries more, for example. Same thing goes when our grid power diminishes. So we are actually exporting again. That power set point will react to this, and it will discharge the batteries less. So this is what will happen here. So that is the first two steps. So we have our grid power that comes from either the net meter or the two converters in parallel. And then we have defined our power set point. Now we need to apply that power set point to the actual converters. But before we can do that, there are a couple of constraints that we should take into account. One of them is our battery charge and discharge limit constraints. So we want to make sure that this power set point that we are actually applying to the converters and applying to the battery, in fact, is not exceeding the charge and discharge limits. So what we can do is, let's apply battery constraints here. So we want to make sure that we get the charge limit of our battery and we get the discharge limit of our battery. And I've defined our helper function in order to get this. So charge limit and discharge limit is a function. So we get it from the battery limits function, and we'll execute it here. So once this function is executed, it will store your charge and discharge limit over here. So this is the get grid power limits, get battery limits function. So we still need to implement it, but the purpose of this is it will return the charge and discharge limits of your battery. Your battery can either will report the charge and discharge limit itself, and we can return that, but we can also make sure that we return charge and discharge limits based upon the state of charge of the battery. And why we want to do that is, even though the battery can still discharge, if we reach a certain minimum SOC, we don't want to discharge the battery any further. For example, our threshold is set to 20%. We don't want to discharge the battery any longer when it reaches 20%. Then we can say here in this function, when SOC is below 20, then discharge limit should be 0 and you should not discharge anymore. Same thing goes on the other side is, if your battery still reports that it can charge, but we reach a maximum state of charge of, let's say, 90, that's something that we define. We say we don't want to charge anymore. So we can define here this function that when the SOC is above this 90% threshold, we can set the charge limit to 0. That's what we'll do here. So I'll have I first want to get is the state of charge of our battery. So in order to do that, so we use the same structure as before. We do cell.app.get measurements. We type in a device ID, which would be the battery ID. And we want to retrieve the state of charge, which is defined in my address at measure.port1.soc. I do want to take an integer and float of this to make it to make sure that it's an integer value. Same thing I have to do here as well in my previous function. I have to make sure that I get the float out of these values. Same thing here when grid power is defined by the power of my both converters. So let's add it here. Okay, so that is the state of charge. Now we can retrieve the charge and discharge limits of our battery. So if our battery reports a charge and discharge limit, we want to do the same thing, self.app.get measurements from our battery ID. And I still need to define it as a constant at the top. And the register name in order to get this is measure.ports.port1.power.charge_max. So this is how I define. Again, I mentioned this during the previous hands-on lab. These register names are arbitrary. We like to use the measure dot and use the dot notation for defining our registers, but you can use underscores between. This is completely arbitrary and up to you to define yourself in your address maps. Then same thing goes for the discharge limit. So let me copy and paste it over. Because instead of measure ports power charge max, I want to use discharge power max. So we have our charge limit and our discharge limit, and we get it from the battery ID. Let me also define my battery ID at the top. It's called battery 1. Okay. So we have our charge limit and discharge limit reported by the battery, but now we want to make sure if our SOC is larger than, for example, our max SOC. What we want to do is we don't want to have that our charge limit is the battery reported charge limit, but we want it to be 0. And then same thing goes for our on the other side. So if our state of charge is smaller than our min SOC, when that happens, I want to make sure that the discharge limit that I define is 0. And again, this max SOC and min SOC are some constants that we can define up here. So we have our max SOC, and let's put it at 90% at this point. And our min SOC, let's put it at 20 for now. So we've done that. So we used our state of charge limit and discharge limit. What we now need to do, so it will return the charge and discharge limit. So we need to return, and I'm going to take the absolute values of this. So we return the absolute value of our charge limit, and we'll return the absolute value of our discharge limit. Now we're done with this function too. So this function, based upon the state of charge, based upon the charge limit and discharge limit of your battery, it will return the charge and discharge limits that we then can use right here in the next part of our execute function. Because like I said, we want to make sure that the power set point that we're effectively sending to the two converters respects the battery limit. So if my battery limit is, let's say, either 0, because I've reached a certain maximum or minimum state of charge, I want to make sure that the power set point I want to set is not exceeding that limit. So what I now want to do is we're going to limit this. So we'll assign that self.power set point again, and we're going to use the limit function in this case to define it. So I have a limit function as a helper function. I've already defined it here. What it will do is it will get the power set point in this case. It will get the minimum value and the maximum value, and it will return the value that's within these limits, within the minimum and maximum limits. So that is what this function will do, and we'll use it here as well. So the new power set point will be the limit of the power set point itself. And with sign convention, I need to type in minus the charge limit and the discharge limit. So this will now make sure that our power set point is always in between the charge and discharge limit. Okay. So far, we have defined our bit power, we've defined our power set point, and previously we also made sure that the power set point is within our battery limits. Next thing is we need to divide this power set point over the two power converters. So what I'll do is power set point per converter is actually, since I have two converters, I can easily divide it by 2 in this case. So, for example, our power set point is 20 kilowatts. We want to make sure that 10 kilowatts is assigned to one converter, the other 10 is assigned to the other converter. And then same applies here, actually. So we in the previous step, we made sure that our battery is respecting its charge and discharge limit, or that power set point is respecting the charge and discharge limit of the battery. But we want to also make sure that this new power set point per converter is also respecting the converter limits. And in the final step, we then will set or send this power set point to the actual converters. So I also have a function for that, and that is the set converter power function, and it will uses a converter ID or device ID as a first argument, and that power set point per converter as second argument. So let's start with the first one. So we'll do it the first time for converter ID 1. We'll go to that function. What this function needs to do, it will clamp or limit that set point to the converter limits, and then it will send that command. So again, same thing here. In order to clamp that set point, we first need to get the import limit and the export limit of that port of the converter where our battery is connected to, because we want to respect that limit, that converter of that port. So the import limit, how we can define that or get that is we'll use the get measurements function again, the built-in get measurements function. So we'll use the same structure as before. So we'll have the get measurements, and we'll type in the device ID. But since I'm using this function, which I can reuse for the second converter ID, I can use the argument that is given with the set converter power function. So I can use converter ID in this case to get the import limit of this specific converter. And the limit itself I can get or retrieve from this register name measured at port of port 2, because our battery is connected to the second port, which is measured at port 2 dot power dot import dot max. And then once we have the import limit, the export limit is straightforward. So it's the same as this. So I'll copy and paste this, but instead of the import power, and I made a mistake here, instead of the import power, it will be the export power that we need here. So import power, export limit, limit, and import limit we have now defined and returned from the device. Next thing that we want to do is again use that same limit function to limit that power set point to respect the input and output limit of that converter. So again, that limited or clipped set point, let's call it that. What it is it uses a self limit function. We'll type in the set point because the set point is the one that we are actually want to limit. We'll type an export limit as the minimum value. We will type the import limit as our upper value. And in this way, our power set point per converter, so for example, in this case was 10 kilowatt, should be respecting the import and export limit. So in this case, on our converter, the import and export limit should be set to 30 kilowatts, so it won't limit it. But if we were to reduce the import and our export limit to, let's say, 5 kilowatts, this limited set point will be updated and will be within the 5 kilowatts limit. And then as a next step, so we have now defined a set point that goes to each converter. We will, or we need to set or send that command to the converter itself. So, and I have another function that does that, is the power function. And what we can do is, again, we want to, the set power function requires a device ID as an argument and also the power set point. But since we're already using this set converter power function where we use converter ID, I will forward this converter ID argument and I will send with it that limited set point that we've defined here in this function. And then in the next function, we'll actually send the limit set point to the actual converters. Let's move to the top one more time, because I said in the beginning I only did this for converter ID 1. Of course, I need to set this converter power to the second one as well, but since I'm using generic functions, again, this function requires a converter ID and a set point. It's really easy to reuse these functions. Even if you have if you were to have multiple or more converters in parallel, let's say 4 or 8, you can use that same function or iterate over each converter and use that same function to actually send that command over to each and every converter. Let's move back down. So we have that set converter power. We've defined our set point that goes to each converter. Then this next step is actually send this command to the device. And the way we can do this is this will use the other function that I've not discussed yet. So remember, I discussed the get all measurements function and the get measurements function to get all the measurements from the controller and the devices that the controller is controlling. Another function that we have here is a set commands. And how it works is it's a set commands function. It also requires a device ID and as an argument, and as a second argument, it requires a dictionary of commands. So commands can be singular. It can be like converter 1 dictionary control.port port 2 voltage is 350. But it can also be multiple commands all at once. So we have our app.set commands, we have our converter or device ID, and as a second argument, we have our commands here. These are just illustrations. So we have our control ports, port 3 method set to constant power, and our port at 3 power is set to 5,000. So this is exactly what we're gonna do here as well. So we'll define a commands dictionary that has these two commands. So first of all, like I said, the battery itself is connected to the second port of the converter. So what we'll do is we'll do control.port.port2 dot method, and I want to make sure that the controller on this port, on the batteries port, is set to constant power. So that's the first command I want to send. As a second command, I want to send that actual power set point that we defined earlier. So for that, we do control.ports.port2.power. And what we do is we create a string out of that power set point. So these are the commands that we're going to send. The port2 method, which is set to constant power, and the port2 power, which is set to the power set point. In the final step, I need to send these commands over to the converter itself. So we'll use a set commands function, which as an argument use the device ID. Same thing goes here because I'm using that set power function, which uses the device ID as an argument. I could just pass it forward because in this case it will be either converter ID 1 or converter ID 2. And then as a second argument, it will use this variable, which is a dictionary, which is the list of all the commands that I want to send. And this command will actually send the control commands to the actual converter. So with this, so now we have implemented all of our functions. One thing that I should mention though is you see that I've already done this before, is the disable battery port. Because as soon as you, for example, you've run the script, you've tested with it, and you close it, you want to make sure that when you're closing it, you want to make sure that you're not charging or discharging your battery anymore because it's not controlled by your algorithm. So I've implemented this before, and where it is used, so that disable battery port is used, is, for example, when I do a keyboard interrupt, meaning I will shut down this local application. Before I do that, before I actually close this application, what it will do is it will first disable and put that these power set points that we're sending to each of these two converters and set it to 0. What we also do is we'll disable the port. So we'll change the port method of that battery port to idle. And if we look into the function, what's happening here is it's what I've been explaining. So it's control port2 method. It will set it to idle, and it will make sure that this port2 power set point is also set to 0, making sure that we are not charging or discharging the battery anymore. And then, of course, we will iterate over the converter ID in this list, meaning, and then we'll do the same thing here. So it will just use a set commands built-in function to send these commands to the actual converters. With all this set up now, we're ready to start testing with this application. But what I also want to do is first is add some print statements as well, because right now I did not yet add any print statements. So it's hard for us to tell what the system is doing, how it is performing. So I'll add some print statements here as well in order for you to see what is actually going on and how the system is performing with our application. I'll build it. Same thing here. So I'll print the grid power for us. And we can see what the grid power is at any point in time. Remember, with the self-consumption algorithm, we try to make it close to 0 so that we're not importing any power from the grid. Another thing is here, I want to make sure that I'm able to see that power set point. So Let's add this here. And we'll add some more. I have it here. I want to make sure that I want to print the battery state of charge. And where do I want some other? So I have this. Okay. Okay. We are ready to run this application now. Make sure that I'll be connected to the lab. Maybe let's get a let's see how the lab actually is performing right now, and we'll see the effect of our application algorithm. So what I'll do is I'll open our Grafana here, which contains our visualizations. So what we're seeing here now is we have our loads, which is around 12 kilowatt of DC loads. We have a little bit of solar here left. The rest is now coming from the grid. So we still are importing 11.4. So with our algorithm that we've now developed and defined, we want to reduce this grid import to 0, and we will use the battery to cover these DC loads. So let's put it. Let's put this to the test. Let's clear this one. Let's run the Python. So in order to run this application, I did not mention this yet. In order to run this application, so it's a Python application. If you open your terminal in your Visual Studio Code or your Windsurf or any other code editor that you have, and you have Python installed on your laptop, you can easily run this application from your terminal by just typing in Python self-consumption algorithm, self-consumption boilerplate .py. So as soon as I do this, I want you to look close about all the print statements that I made and make sure, and especially look at the grid power that we have. So we want to reduce that and minimize it to 0. So let's start the application and see how the self-consumption algorithm responds. So, okay, battery state of charge 29, with input power 11.97 kilowatts. In the second iteration, we reduce it to 500 watts, and we see that the set point that we send to our both converters are this. So, and in the second iteration, it's only 500. The third one is only minus 220 watts, 50 watts, 40 watts, 30 watts. So we're actually limiting or minimizing the grid import now. So we came from our set point where we're still importing like 12 kilowatts before we started the self-consumption algorithm, where now our grid import is effectively 0 or 20 watts. And we're still using the battery power to cover the loads. And if I open our Grafana again, our visualization, this is also reflected here. So this is again this is our live lab right here that is working. So you see before that we were still importing from the grid to cover our DC loads, and whereas right now our AC load has shrunk and is almost 0, and our battery is now taking over and is supporting the DC loads in this case. So this means that our algorithm or application that we've developed right now is working.
Meanwhile, the loads, were they affected by this change?
No, not at all. So the load stayed on.
Yeah.
The load stayed all the time. So there was a question in the audience here. So no, the loads stayed on all the time during that phase. So it is, so what the power set point was applied to the converter, instead of importing it from the grid, it's now requesting that from the battery. So the power set point changes, and the converter now in this point, in this case, was supporting the DC loads. There was no blink at all in this whole system. This is a smooth and a smooth transition in between this. Yeah, and remember that I've said that we have the. Let me go back to my application one more time. So this one is still running now. So let me quickly exit this program. Remember, in the start of this demo, I said in some of the applications that you might be writing, you do have AC loads, and you want to make sure that your grid power is measured from your net meter. So if you also have AC loads, so let us run that scenario 2, where we have our net meter as the active monitoring. So remember, I set this net meter active to false, but if I set it to true, let's see what happens then. If I restart the application, so that this grid power before was the sum of the AC, the sum of the converters. Right now it's from the net meter. So, and we see again, we start with like almost 14 kilowatts that we're importing to like 3, and right now we're diminishing the grid import here. So you can see it's 68 now, and our power set point is divided over our batteries, or over our converters and our batteries, in fact. So that's what's happening here. So both algorithms work with both the net meter and where we, in the application where we don't have a net meter, where we rely on power from the converters. One more thing that I'd like to test here with you on the spot is, I've not done this before, but of course it should work that way, is since we have our battery's low state of charge, let's say that our minimum state of charge is 30. Our battery, which is at 29 at this point, so what we want to see here is that our discharge limit is set to 0, and which means that we effectively cannot discharge a battery any further. So what I want to see here when I run this application is the battery just staying idle at 0%, at 0 watt, and that the DC loads are still powered from the grid. So let's run this application one more time. Okay, and I think that's what we expected. So our grid power right now, it's 14.7 kilowatts. Battery state of charge is 29. And it's set that our power set point is 0 watts in this case. So, and the power set point that we're dividing over the two converters in this case is also 0 watts, which is what we would have expected. So this means that the algorithm is running as intended. And is working flawlessly. So good. I do want to, so this almost concludes the demo. I do want to point out a couple of things. Whereas this is a complete and a good algorithm to start with, this algorithm might not yet be complete, as in there are some things that we still need to take into account. So for example, I assumed in this application that our converter was already set, or the DC bus port of our converters were already set to 350 volts. So I didn't take this into account. So what I also didn't take into account here is when I set split power between the two converters, I set I was under the impression that both of my converters were working and actively converting power, but it might be an application where one of your converters faults. So better way to put this is add another function here that says get active converters, where you define a function that, for example, can check for each and every converter that you have. Is it online? Does it have a communication issue? Does it have any fault or errors? Is it actively converting power, for example? And that function will return a number of active converters that you have in your system. This is to make the system more robust. So this is for this demo purposes. I assume that both converters were online. But this is a way to make your system more robust. Also, for example, I didn't take into account any pre-charge that might be needed to connect your battery. So that prior to charging and start discharging and charging your battery, you might need to connect your battery to the converters, and you need to do a pre-charge. So that will be a step before we actually go to the self-consumption algorithm. So whereas this is a complete working and functional code, which shows the self-consumption algorithm, I should say that there are other things that can be done to improve this function and this code. I think that concludes my presentation and my demo for today. I'm now wondering, are there any questions from the audience? Have there been any questions so far? I'm looking at Dusan and Matt from the.
I guess I joined a little bit late. I think that function limit that you were talking about, like this active converters, do you like an overview of the built-in functions?
Sorry, which function?
I think get active converter.
Yeah, so that's what I was saying. So the question was about get active converter. So previously, for my demo purposes, I assume that it is. So I know that I have two converters in my system. I assume that they were online, and for this demo purposes, this is fine. If you were to like improve your algorithm, make it more robust, and make sure that it works in every circumstance, what you should do, or what an improvement could be, is instead of defining the two right here, is create a function that returns the number of active converters that you have in your system. For example, like this. And what it will do, so I can define it here. And what it can do is, so for example, it will iterate over, for example, all your converters. And it will check for each converter. Let's do this. And let's do this. What it can do is we can say, are there any faults? If there's any faults for each converter, then we'll say the number of converters that we, so we can say number of active converters is 0. So we start from 0. If there are any faults, then we don't add this converter as an active. If it doesn't have any faults, what we can do is number of active converters. We'll say, okay, we'll add it with 1. So that is something that you could do in order to improve this algorithm and make it more robust. So if it has any faults, you can check for is it converting power. So these are all things that we can do in order to make sure that we have the actual number of active converters here.
There's a question in the audience.
Okay.
It says, what is your philosophy in actions that you take to test edge cases where you simulate failures?
what is my philosophy? So of course, definitely testing. Testing would be the first one. We gain a lot of experience by having our own DC lab out here. And have the equipment up and running in a test environment where you can go over this scenario one by one, and get familiar with the devices that you have. That is from experience. You have to know a converter, you have to know a battery, you have to know its operating sequence. So it's testing in a control lab environment. And of course, we already have defined some of these constraints already. So like the minimum maximum state of charge, but minimum and maximum state of charge is only one. You can also look at your actual voltage of your battery as a second measure to make sure that you don't overcharge or over discharge your battery. So looking at state of charge, looking at voltage is one, and so on and so forth. It's control lab environment and getting to know the device.
And I see this as being coded in like, yeah, Copilot, can you, I guess, Windows, so can you use Copilot to help you out coding today, or what's sort of philosophy on using AI with this?
Yeah, that even improves you, but for this lab demo, I didn't want to turn on the Copilot, but if you use any code editor like Windsurf or Visual Studio, what you can do is it will autocomplete some of your functions. So it might be able to tell me to autocomplete this function for converter ID in, let's see if it's smart enough to make sure. Okay, so this is what it can do. So I didn't have to return this, but it was able to say, okay, number of active converters 0, and as soon as there is a fault, or if fault is 0, for example, we'll add this. So
this is like a superpower. That was really fast.
This was really fast. So I was struggling before typing it in, but Copilot was helping me tremendously defining this function. So yeah, Copilot, any other code editor that uses a AI integrated code editor, then yeah, it's really helpful. This helps you develop applications at a real high speed. Yeah, very fast.
Thank you.
Are there any other questions from the audience? Yeah, there's one here.
How can I find more information about the controller?
So to find more information about the controller, so you have to go on our website. So we've launched our new website. So Dusan already showed it in one of his previous presentations. So if you go to directenergypartners.com, so this is our improved and new website. So all of this information can be found here in the microgrid controller part. So this is where you can find all of our information. You can also discover pricing and also request your starter kit here. So if you want to start coding yourself, we have starter kits available. So you can go get your own starter kit and start coding and configure your own setup yourself. And yeah, for more information about any other features, the core integration feature, also the case studies that we've done before, yeah, go to the website, directenergypartners.com/controller, and you can find more information over there.
There was a question earlier that got answered about how do you get to the PPL code base repository? Maybe you can clear how you get there.
Oh yeah, of course. Best way to do it is, like I said, I mentioned it before, the documentation is the best way to start. In order to get to the PPL app repository, you can go to custom applications right here. And if it brings me to this page, you can see here the PPL repository. Under fork repository, you can see that this is where we have the DP PPL app. If you go to click on this link, this should link to the PPL app. Oh, this is the one, the PPL app repository. This is the one that you need. So it's a publicly available under Direct Energy Partners, but it's publicly available. You can start forking and creating your own copy of this repository. So way to go to this is go to documentation, go to custom applications, and under fork repository, you will find this PPL app repository.
One more question. There's it's my understanding that if you have your own controller hardware, you can also get our app from Phoenix Contact's App Store. Can you show us how that's done?
Yes. So since we're partnering with, we're using the Phoenix Contact controller and all is Phoenix Contact based. We have, and since the OS, the operating system is all packaged in an app container, you can also go to, this app is also available on the PLC Next store, which is like the app store for iPhone. If you go to app installation, so go to installation and under app installation, the required apps is, so one of them is a Mosquito MQTT broker, but the other one is a Power Platform app. So if you click on this link, you will be directed to our application, our OS that you need to install on the controller. And yeah, you can start working from there. If it directs me to this page, that would be good.
So this is the official PLC Next store?
Yes, this is the official PLC Next store. Say definitely go try it out yourself if it won't load. Too many tabs open at this point. Oh, here we are. Still rendering. But anyway, yeah, this is the official PLC Next store where you can download the Power Platform app from sort of OS. So it's a 1.0.0 version, so you can download it here and install it. So all installation steps are included in the documentation. So yeah, here we are. So this is the PLC Next store with the Power Platform app right here. Okay. Yeah. Okay.
That's Power Platform give you the possibility to set up user interface.
Yes. So questioning from the audience is the controller, does it come with like a UI or how can it be controlled? So naturally the controller comes with a local UI, and this is the one. So this allows you to also control and see a snapshot of your system from the UI as well. So you can from this page change your operating modes. So the control itself comes also with predefined applications like or operating modes like the manual charge discharge, the manual peak shave, the planned operation, and all can be controlled from this local UI. Battery settings, converter settings. There's even an O&M page that gives you an overview of any alerts, any past alerts, any status of your devices that you're controlling. So for example, the converters, the batteries, the net meters, it's all running here. And it can also give you, it will also retrieve you the logs. If there's anything wrong during setup or commissioning, you can check the logs in here and see if there are any issues here. Yeah, okay. I think that's it. We'll conclude this demo. We'll resume in like 40 minutes, Dusan, is that correct? So in 40 minutes at 3 p.m. Eastern, we'll resume with the lab tour, so the live DC Microgrid walkthrough. So I hope to see you there. Stay on if you want. Yeah, and hope to see you there in 40 minutes lab tour. thank you so much for attending, and I'll see you in 40 minutes.